Okay, so we've got another question in this section, and it's about, again, having two diagrams and two things. So in part A, we've got a diagram of a table, effectively, and I'm going to put the book on top of it as well. And then we've got a diagram of, I'll just do a table, what was I going to do, just a book. In fact, I'll put both in, both cases, but we'll just do it separately. So here we'll do forces acting on the table. Here I'll do forces acting on the book. So the table has got its own weight, so that is 65 G. Okay, and it's got 4 legs, and each thrust is the same. So we've got 4 legs effectively. I'll just put a couple in. I know that obviously it's a one-dimensional diagram of a three-dimensional thing. So each of these legs is given the same thrust of just what we're calling T. Okay. Somewhere, force the floor is giving effectively. They're calling it thrust. Technically, it's actually another type of reaction force. It says here, set the magnitude and direction of the force ground. I know, thrust in each leg. Okay, so also we've got. Let's just look at the other diagram for a second. The book, which has got its own weight, so it says quite slightly confusing here. The mass is given in grams, so it's 0.26 kilograms. So actually, the force is 0.26 g. Grams and g for gravity, not the same thing. But we also should know, I'm confident with this reaction force that's in here. So the book feels the table pushing against it, which means actually over here, the table has got a force, which is the book, the feeling of the book pushing down on it, which is not the 0.26 g per se. It is if it's not an acceleration, but it's just the reaction force. Okay, right, so that's part A. Just pause that so I don't know if that makes sense, having started, or if it started from again. Thrust in each leg. So if we look at this diagram here alone, we can't get anywhere because we've got two unknowns. So we'd have to do a whole system. Now this question is in equilibrium because it's just a book sat on top of a table. So you could just say, you could take a direction to be positive and do F equals ma. So for the whole system, it would be 4t, and the question wants that you do it as 4/7t, plus r, minus r, and then minus 65g and minus 0.26g. And because it's an equilibrium, it will be equal to the combined masses times by, well, 0. So it's 0. Or you could say, well, it's clearly in equilibrium. I'll just say that the forces up equal forces down. So you'd have 4t plus r equals r plus 0.65g, sorry, just 65g. Give me 0.5 in the wrong place, 0. in the wrong place, and then plus 0.26g. And actually, again, in either one, you can probably clearly see that the need for the r's is they're going to cancel out anyway. So if you use, for example, the equilibrium, which this one will just rearrange to underneath, you'll get that 4t equals to 639 point something something, and that t will equal to something around to 160 newtons. So the thrust in each leg, which is why it's important you split into the t's. Again, this is just really a reaction force. I know they've got it thrust, but it's kind of reaction between the ground and the object. And then state the magnitude and direction of the force exerted on the ground by the tabletop. So on the ground by the tabletop, so it will be effectively equivalent to the 4 thrusts. So it will be kind of this idea with 4 thrusts. So in the way that reaction, it would be these 4 and then 40 going down. So it would just be the 600, and I think this rounds to 640. 640 newtons downwards, effectively. Okay, so again, another opposite and equal reaction force there.